And Jorge, if you'd like to share your screen. All right, so today's talk is going to be about CC DNI campus design for northern New Mexico, and Jorge has agreed to be the speaker for today. So I will turn it over to him now. So go ahead.
Thank you, Jason. Good afternoon. I'm Jorge Crichigno. I'm currently at the University of South Carolina. But this work was conducted when I was at Northern New Mexico College. It was a CC Star project to deploy a Science DMZ. So I will present what we did at Northern New Mexico College and the undergrad research opportunities that this project opened. So first, NNMC, Northern New Mexico College, is a very small college, about 30 miles north of Santa Fe, the state capital. So it's an under-resourced institution, and for example, there was no network engineers. So myself and the IT director at that time, we led this project, and with the help of the students. NNMC has an information engineering technology program, IT program, and with the help of these students, we were able to complete this project. So this project was conducted between October 2015, December 2017. So it just expired about a few months ago. This slide shows the big picture of the project. First, we needed to upgrade the border router. Previously, the border router was a Cisco 2800 series, very old router. And we put in place a new border router. Second, there was a need for upgrades to increase the intra-campus transfer from 100 meg to 10 gig. Most of the campus network and still part of the campus enterprise network, the regular network, runs at 100 meg. But the research network that we put in place, the Science DMZ, is right now 10 gig. So we deploy a Science DMZ and the research network. There is connection to 4 buildings. I will go in more details that serve science and engineering. And finally, this was not part of the grant. This was not part of the project, but this is a consequence of this project. IT and the president and the provost, the vice president, decided that we show a case that we needed better connectivity to internet and have access to internet too. So they promised to increase the external connectivity from 100 meg to at least 1 gig to the Albuquerque Gigapop. That is the only, and again, that was not part of the project, but this is the only part that was not finished when I left the institution in December 2017, but is projected to be in place in this year, 2018. This is the before and after. On the left-hand side, we have the before, the campus enterprise network, the regular network. Switches running at 100 meg, is behind a firewall, and a very old router, Cisco 2800. This is what we did with this grant. We upgraded the border router. It's running at 10 gig. The research network is in place. That means new switches for the research network, access layer switches, aggregation switch, DTNs. There are connectivity, high-speed connectivity to labs, and also something that was not part of the grant was to put in place a storage area network for research. So we were able to obtain funds from the EPSCoR project, and we put in place a storage area network in the research network as well. Previously to this grant, to this project, there were connectivity at 1 gigabit per second, the backbone of the campus, multimode fiber between some buildings, but access switches were running at 100 meg and even some in some buildings at 10 meg. Again, right now we have much better infrastructure, in particular in the research network. Single mode fiber, that was a very large portion of the project to deploy single mode 10 gig across campus. On the left-hand side here, we have the topology and how we deploy fiber between 5 buildings. First, the administration building where the border router is, then vocational education building where the data center is. That's the place where we put the aggregation layer switch. On the right-hand side is the topology of the Science DMZ. Then the storage area network is also attached to the data center, and the different science and engineering buildings. Those are the distance on the left-hand side. We can see the distance between buildings. Now on the right-hand side, first the border router is new, the aggregation layer switch as well, and the access layer switches. All those devices are new. All this network is new actually. And again, the SAN is being used for research only and was bought using EPSCoR funds. We have DTNs per sonar and connectivity to research labs. The one that is most heavily used definitely is the biology. One of my co-PIs was from biology. And for research purposes, biology is the one that used the most. Now, I will talk about the IT part and what type of opportunities this project opened for IT students. I teach in the engineering and technology. I used to teach in the IT program there, and I was very interested in this part. And before I go to that, I will just point out what ABET is the accreditor for engineering and engineering technology programs in the country. What ABET says about engineering technology programs. So those programs usually focus on application and implementation. So this was really a great opportunity for applied research. So next I will talk about 3 projects, if the time permits, 3 capstone projects. I taught capstone projects at Northern Mexico College, and we use many of the ideas, we apply many of the ideas that I brought from this project and also from some workshops that I attended when this project was going on, for example, the OIN workshops. The first one is about TCP BBR versus window-based, loss-based congestion control. We wanted to explore, some students wanted to explore the effect of maximum segment size and parallel stream on big flows. Very brief overview about BBR. This is the newest congestion control protocol. The paper was published in 2016. And according to the authors, this congestion control protocol represents a disruption from the traditional window-based, loss-based congestion control used during the last 3 decades. So BBR used pacing to try to match the bottleneck rate, and the paper is really nice. The first one at the bottom has a much better explanation. On the right-hand side is a very basic explanation what BBR tries to do. Now, what we wanted to do is, because this is a new congestion control protocol, we wanted to see how BBR performs when transferring big flows. And in particular, what is the impact of the maximum segment size and the use of parallel streams on BBR when compared with the traditional congestion control protocols. So why is important to have a segment size large? Because it produces a faster recovery after a packet loss. On the left-hand side, this is the typical behavior of TCP. We have the congestion windows, how they change over time when there are packet losses. Well, the main difference or the impact why MSS, maximum segment size, is relevant is because during the additive increase, the recovery is faster. The slope of that rect is faster, basically. On the right-hand side, we have the equation that follows the TCP throughput, and this is for TCP congestion controls that are based on packet losses. So BBR does not adhere to this equation. But that's something that we wanted to see in practice. The other factor that we wanted to research is what is the effect of parallel streams. Why is this relevant for Science DMZs and big flows? Well, the use of parallel streams or parallel streams are used, for example, for Globus or other applications that are for big data transfers. Essentially, the idea is that opening parallel connections creates a large virtual maximum segment size on the aggregate connection. In this case, we have 3 connections. The aggregate work as a single connection with larger segment size. So this is the scenario that we use to test the performance. We put in place a sender and a receiver connected by a 10 gigabits per second path, 20 milliseconds round trip time, running CentOS. We use iPerf3 memory to memory test, and we use Nethem, which is a Linux package, a Linux software that emulate wide area networks to adjust the loss rate. So we decided to use just 20 milliseconds because at this round trip time, throughput already collapsed when it's subject to a small loss rate. On the right-hand side, we have this figure from Eli Dart's paper, and if you notice, if you check, you can see that at 20 milliseconds, the throughput typically already collapsed. With a very low packet loss rate. On the left-hand side is our topology, the sender and the receiver, 10 gigabit per second path, 20 milliseconds round trip time, and we use Cisco switches 3172PQ. Before I present the results, just one word about emulation versus real networks, and I will point out a work by Michael Smith-Asin and Brian Tierney, and they are very responsive. When I was learning about this tool, they respond to each email. Emulation using the network emulator works very well. According to their results, the results on real networks, for example, ESNet test, and emulation networks are very consistent. So that is one of the reasons why we decided to use Nethem for this test. So each experiment lasted 70 seconds. The first 10 seconds were not taken into account to avoid any transient behavior. And for each test condition, 10 experiments were conducted and the average throughput was computed. So this is the first set of results that we got. Figure number 1, we have throughput versus maximum segment size. And we have BBR versus some well-known loss-based congestion control algorithm, HTCP, Cubic, and Reno. Again, we wanted to study the effect of maximum segment size and parallel streams. So from the first figure, it was clear to us that the impact of having a large segment size is even stronger in BBR. Even though all the algorithms improve when the segment size increase, the improvement in BBR was larger. The figure number 2 is the same information, but is the performance of HTCP, Cubic, and Rhino with respect to BBR. For example, the blue curve, HTCP, the performance of HTCP is between 10 and 40% lower than that of BBR. So basically, all the other algorithms perform worse than BBR. And when the segment size increase, apparently for us, and I will show the following results, the gap between BBR and the rest increase. Now the figure number 3, this is what happened when we use parallel streams. And I forgot to mention, this is with a corruption rate of 0.001, very small corruption rate. Well, using parallel streams increased the performance of all the algorithms. Few observations that were interesting for us here. HTCP, Cubic, and Rhino, those based congestion control algorithms, they all have similar performance when parallel streams are used. So that was the first observation. The second observation was that, again, BBR performance the gains of BBR are even larger than that of the other algorithm. In this result, it's not that clear because BBR performance is being limited by the network bandwidth. BBR very quickly get to almost 8 gigabits per second with a maximum segment size of 1,000. So that's the only limitation of BBR there. However, in the next results, when the corruption rate is 0.01, we will see this more clearly, how parallel streams improve BBR performance even more than the other algorithm. In this scenario, we have a corruption rate of 0.01. And first, this is what happened when we have a single stream. The throughput collapse for any congestion control algorithm, including BBR. So when the maximum segment size is 1,000, the performance is 0.5. That's the best performance, BBR. However, again, when the segment size increase, the throughput start increasing. BBR is able to get up to a little bit above 2.5 gigabits per second. And again, what we notice here is that the gap between BBR and the rest start increasing. Now, I will go to the figure number 3. Here we have 10 streams, the same corruption rate, 0.01. And this was a very clear result for us, how the gap between BBR and the rest of the algorithm increase when parallel streams are used. BBR start with about 2 gigabits per second when the maximum segment size is 1,000, and it goes all the way to above 8 gigabits per second. On the other hand, HTCP, Cubic, and Rhino, they can get about between 2 and 3 gigabits per second maximum. Again, some observations here. The performance of loss-based congestion control algorithms are very similar between them when parallel streams are used. Figure number 4 has the same information as in 3, but with respect to BBR performance. Basically what we have is the performance of HTCP, Cubic, and Rhino is between almost 80% lower than that of BBR when segment size is 1,000, and it doesn't go above 60% lower. In summary of the regarding the previous result, when not limited by network bandwidth, parallel streams improve BBR performance by more than a factor of 3. And I will point out to the figure number 2 here. The figure number 2 shows the ratio of 10 stream to 1 stream throughput. So what this shows is that, again, BBR is able to multiply by 3 the throughput when using parallel streams. Now, the other algorithms are able to improve as well, but not as much. So, for example, HTCP is not able to improve by a factor of 2. It's always the factor is below 2, referring to figure 2. Now, another interesting observation is the algorithm that improved the most among loss-based congestion control is Reno. So that reinforced what we were observing, that all the algorithms based in loss congestion control perform somehow similar when parallel streams are used. The second item, the improvement factor for loss-based congestion control is always lower than that of BBR. When parallel streams are used, the performance of HTCP, Cubic, and Reno are similar. I will spend 1 minute on this result. We conducted many more tests on BBR and comparing with those of HTCP, Cubic, and Reno. But I will just focus in number 2 and number 3 here. Number 2 show what happened when parallel streams are used. And on the x-axis, we have the corruption rate. On the y-axis, we have throughput. So what this results is showing us is that BBR is able to sustain the throughput even though there is almost an order of magnitude increase in losses. So when the rest of the algorithms start decreasing the throughput drastically, BBR is still able to sustain the throughput. Similar results are seen when the maximum segment size is increased. This is shown in figure number 3. So both factors, parallel streams and large segment size, help every algorithm, but it helps BBR the most. So that was one capstone project. I will briefly talk about another project, traffic characterization using Netflow. So the motivation here was the following. We put in place, first, Northern New Mexico College didn't use any monitoring before this project. Now, the border router was acquired, and this border router had Netflow capability. So flow statistics were available. Also, according to the literature research that we did, flow-based IDS are more scalable than payload-based IDS. There is a very good tutorial that I'm pointing out, reference number 1. And the goal of this project was to characterize normal flow behavior. We didn't want to inspect any payloads in the packets, but only the flows. What can we do with these statistics? So one approach to characterize flows is to measure the randomness or uncertainty of elements of a flow. And here we have an example, our campus network and the internet. And we have a bunch of flows. And what we would expect as a normal behavior of a campus network, at least a small campus network as ours, was that most of the connections had the source port equal to 80. Why? Because most of the students on regular time, they will connect to websites. They use HTTP port 80. And we could have few source ports different than 80. For example, we have port 22 in this example. So one approach to measure the uncertainty was by using entropy. And entropy is just a metric given by this formula on the top. So for the previous example, when we had 5 flows connected from port 80 on the internet and 1 flow connected on port 22 on the internet, applying that formula will give us an entropy or uncertainty of 0.65. Now, an entropy 0, if we apply for any case, we apply this entropy concept. An entropy 0 would mean no uncertainty. So, for example, if all the connections were to port 80, we would have entropy 0. Now, on the other hand, if there is a lot of uncertainty, if all the ports were different, we would have an entropy of 1. So what we did is we used the border router as a metering point. We collected inbound traffic. So what that means is that the source IP address is in the internet, the destination IP address is on campus. And we use a collector, and the collector organizes the flows in 5-minute time slots. So for every time slot, we compute this number entropy. And then we characterize, we start trying to find patterns. So this is an example of a typical week. Here we have the entropy of the source IP and the source port. On the right-hand side is the source port, on the left-hand side is the source IP. Start with the Saturday, March 25th, and end with Friday, March 31st. And few observations of what we found. In general, for the source IP, the entropy is high, is about 0.8 average on weekends, and it lowered to a little bit above 0.7 during the weeks. And that makes sense for us because the source IP are dispersed over the internet, so there are so many different source IPs, so the entropy should be high. However, we see that there are a lot of abnormal low entropy points, and it turns out that those are attacks, for example, dictionary attacks or DOS or scanning attacks. Now, entropy near 0, that means that there are no uncertainty. That means that somebody is trying to connect to the network, and the few source IP addresses dominate the distribution. That's an anomaly. On the right-hand side, related to the source port, we see a pattern on the weekdays, very clear pattern. During the weekend, the pattern is not that clear. Higher entropy during the night and weekends. Large volume of HTTP flows when students are on campus. So, for example, on Monday or during a weekday, near noon, the entropy of the source port is very low, roughly about 0.2. So what happened is that most of the students connect to HTTP port 80. So that's what it is expected to have a low entropy. However, again, we observed abnormal high entropy points. For example, on Friday at 0 hours, there is a very low, and there are several. It's not that clear, but if we could zoom in, we would see much clearer some abnormal high entropy points. For the destination IP, on the left-hand side, there was again a clear pattern during the weekdays. In general, there are low entropy, few IP addresses on campus. And this result was not a shock. That makes sense because Northern New Mexico College used network address translation. So there are few IP addresses that are used. Higher entropy on weekends and at night. Lower entropy when students are on campus, in particular around noon, when they are out of classes and they are looking something on the web. So we only use a handful of public IP addresses for regular internet connectivity. Now, on the other hand, with the destination port, we found that there is a pattern. For example, at night, lower entropy, high entropy, very close to uniform at noon. And we start figuring out what was happening at that time. And well, what happened is the dynamic ports are used by browser when students connect to the internet. So if I open a browser and connect to CNN.com, my port will be an ephemeral port, 55,000, or will be like a random number. So that's why we're seeing a very high entropy during the weekdays. Again, we found abnormal low entropy points. There are several low entropy points that indicate that something is happening in the network that are not normal. Now we correlated these results. At the bottom, we have the source IP, then the source port, destination IP, destination port. We come up with a new metric that combined source IP, destination port, and then the total traffic volume. First, the total traffic volume is not a good measure for, at least was not a good measure for us to find anomalies. However, correlating the different features like source IP, source port, destination IP, destination port, gave us very good indicators when an anomaly happened. I will not discuss all the events here. We found several events, but just to give an example, event I, there is a low destination port entropy, high source port entropy, and low source IP entropy. And it turns out that that was a dictionary attack. Low destination port entropy because there was an attack to a specific port on a machine on campus. High source port entropy because several parallel connections were open in the attacker machine. Low source IP entropy, several connections were open from a single attacker. And I will go just 5 minutes. The third example of a performance of capstone project, performance evaluation of virtual DTNs. So the motivation here was virtual DTNs are attractive for some small institutions. VMware is a well-known technology. Virtual machines are easy to deploy on demand. So the question that we had back on time was, what is the performance of virtual DTNs? So two scenarios were considered here. First, and I have here the topology on the right-hand side. Host number 2 and host number 3 are physical DTNs, and host number 1 is a virtual DTN. From host 2 DTN to the virtual DTN located in host 1, that was one scenario. We measured the performance. And from host 2 DTN to a host 3 DTN, that is a native. So we measured transfer from host 2 to host 1 and from host 2 to host 3, and then we compare. So the path capacity in this scenario was 10 gigabits per second. VDTNs use this virtual NICs. This is a virtual NIC by VMware. We use iPerf 3, and we emulated wide area networks using Netflow. Now, the physical limitation in this scenario, and we didn't know this before the test, we didn't know if the physical limitation would be the physical switch or the virtual switch that is inside host number 1. But it turned out that the physical limitation was really the physical switch. So the physical switch has about 8 megabytes of memory for buffering. So for 8 megabyte buffer and 10 gig of bandwidth, the critical round trip time using the bandwidth delay product relation is about 7 milliseconds. So the figure number 1, here we have throughput versus round trip time for 1500 byte segment size. And we have native to virtual results. That is when a native DTN is transferring data to a virtual DTN. And also, we were interested what happened when jitter was introduced. In summary, what figure number 1 is showing is that performance was very similar when conditions are perfect. That means no jitter. The destination DTN is able to process or receive all the frames in order. But the difference was clear when more processing was needed from the DTN because of the out of order reception of segments, for example. And that's what we see in the figure here. The native to native, when there's jitter, the performance is better when we have native DTNs. Now, figure number 2 is what happened when we have 9,000 bytes of maximum segment size, and the performance was very similar in both cases. So in conclusion, this CC DNI project has a very large impact in several regards in this institution. I didn't present here the science impact, but had a very large impact, in particular for biology people. Intra-campus connectivity improved from 100 meg to 10 gig. Connectivity to internet is expected to improve. This is the only portion that is still pending, from 100 meg to 1 gig. A large impact on science research, biology in particular, and plenty of research and hands-on training opportunities for IT students. And I will stop here.
All right. Well, thank you so much for going through all that. So we'll wait a minute here to see if any questions come in. I jotted down a couple that I can start us off with. I think you said it, but how many students went through these various programs?
If I have to quantify the impact, overall is probably above 10. Three students helped me to deploy the Science DMZ. But after we deploy, we start doing some capstone project with more students.
And do you have any statistics about if this was able to help them with careers, or I'm guessing some of the students have graduated at this point?
Yes, again, I didn't include this, but the 3 students were hired by Los Alamos National Lab. After this project, Los Alamos was very interested in what we did, and they came to us, they opened an internship program, and they told us that they wanted to hire about 20 students starting in January 2018. That's the time that I left the institution, but it's my understanding, actually many of my students are writing to me that they are working right now at Los Alamos. Other students, for example, one that we're about to publish 2 papers based on these results. Actually, I submitted, and that's something that I didn't fully finish this project because I said to NSF that I would be publishing, and I didn't, but it has been submitted, and we're about to publish 2 papers with these students, with 2 students. One of them is in Georgia Tech right now using a master, doing a master degree. So that's the what I remember right now, Jason. So it has a very large impact.
Well, good. That's great to hear. So we have a question from Jim. In the VMware trial, what was the model of the physical switch with 8 megabytes of buffer?
The physical switch was a Cisco 3172. Let me go to this. And this switch, as far as I understand, it has a 12 meg of memory, share memory, and up to 8 meg can be allocated to one port. So that's why I put here 8 meg maximum allocated for buffering for one port, but it's a shared memory really.
And did you consider maybe trying additional makes and models in that particular experiment? Is this one that you were going to be publishing information about, or no?
Yes, it's about using this switch. That's a good question. If I will go a few slides and I will respond that. Okay, here, the scenario that we put in place is only 20 milliseconds round trip time for the experiment. There are 2 reasons why we choose 20 milliseconds. First, the first reason is with 20 milliseconds is enough already to see how throughput drastically drops. But the second is we only had switches with 12 meg of memory, and we were not testing the capacity of buffering on switches. We were testing something else. That's why we used just 20 milliseconds round trip time. But we won, and we're putting in place at the University of South Carolina a test bed with more powerful switches, and start testing in much more details the buffer issue. So the answer is yes, we want to test different models and the impact of buffers. We will not publish that. We don't have information at this time, but we will do it.
Okay, and Jim has a follow-up. In some of the performance plots, some of the corruption rates are 0.01% and others are 0.001%. Is this a loss rate that was dialed in, or is it an experimental result?
I think Jim is referring to this slide, number 16, 0.001%. We purposely put this corruption rate because we wanted to see what happened at this and what happened when 0.01 was used. It was on purpose, and the way that we set these values is using the network emulator software. I hope that I answered.
Okay, well, we'll wait for Jim to confirm that. So while you're looking at that slide, was this a specific snapshot of BBR at the time, and have you tried to go back and revisit the results since they've probably released some updates since then?
I didn't go back. I didn't go back to that. These are results that we just got less than a month ago.
Okay, so it's a relatively new one then. Okay.
Yes, yeah.
And Jim confirms that answered his question. So can you go back to the set of slides that was dealing with the virtual DTNs? Okay, so based on this, I know a lot of people are sort of looking into trying to deploy these. do you think that at this stage, you know, the performance of the virtual hardware is really capable of delivering sort of small capacity use of DTNs, and sort of what do you think is the inflection point at which it's not really going to be able to compete?
Um, Based on what we saw, at least 10 gig memory to memory, if conditions are good, that means there are no retransmissions or few retransmissions and few loss rate or small loss rate. It is apparent to us based on this that it is feasible 10 gig. Now, above 10 gig, as far as I know, the virtual NIC that is used by VMware, I didn't see any tests above 10. They clearly show, and there are some paper from VMware that show that they support 10 gig. The virtual switch, let me go one slide. The virtual switch we didn't have any problem with the virtual switch. We thought that we would have a limitation on the virtual switch, but we didn't find any limitation. So the main limitation apparently was the CPU, because when we introduced jitter and more processing was needed by the virtual DTN, that's when results start being different between the native and the virtual.
So when you were doing this testing, were you using just iPerf as the application, or were you using something else?
We use iPerf, and also we did, yeah, I forgot to clarify this. These are just memory to memory, the results that we have here. But we also conducted, I didn't prepare here, I didn't show here, but we also conducted the hard drive to hard drive using Globus. And we didn't find much difference, probably 5% of difference. So that's the penalty of using virtual. But again, that was 10 gig. That's what happened when we have 10 gig. And under perfect conditions, the penalty was about 5% with Globus.
And what was the sort of makeup of the hard drive infrastructure on this on the host machine for the virtual machine? Was it sort of an SSD, or was it still a spinning disk?
I have to go and check, Jason. I will check that and I will answer that. I just don't know at this moment. These are the DTNs that University of New Mexico suggested us. We followed their same model, and I don't have the answer right now, but I can go back and send it to you.
Okay. All right. We'll pause again for a second here to see if anybody else has any other questions they want to ask. I'll thank you again, and if you can send me your slides, I'll make sure that they get posted as well.
Okay. Yes, I will do so.
All right. Looks like we may not have any other additional questions. So thank you so much for presenting this today, and I'll make sure that I get the slides posted and the recording as well. And for everybody who's still on, we're going to have a 1 week pause, and then we'll pick up the week after. So thanks again, everybody. Have a good weekend.
Thank you.